this video lesson, what we're going to go over are wave properties. We're going to start by talking about some of the things that hopefully you saw in your lab regarding wave speed. Then we're going to talk about wave interference and superposition. Then we're going to move on to talking about what happens when a wave bounces off an object, or wave reflection. And finally, what happens when waves go from one material into another. We call that wave transmission. So to get things started, there's two things that I'd like you to know regarding wave speed. One is that the wave speed does not depend upon the amplitude of the wave. The amplitude does influence the energy that the wave has, but it doesn't influence the speed of the wave. If we take a look at the equation that we learned earlier in the chapter, V equals frequency times wavelength, what we see is that there's no amplitude term there. So while the amplitude may, if you have a 10-foot wave and it crashes onto the beach, then it'll definitely do some more damage than a 2-foot wave, but the speeds will be the same. What does influence wave speed is the medium that the wave travels in. This can be represented by the tension. You change the tension a little bit in your slinky or coil lab, or the density. If sound travels from in a less dense or more dense material, it will cause its speed to change. So summing things up with wave speed, the amplitude will not affect the wave speed. It does affect the energy, but the wave speed does depend upon the medium. The second part of the wave lab demonstrates a property of waves known as wave interference or superposition. And this occurs when two waves are going to meet or pass through one another in the same region. So if we imagine a wave coming from the left, we'll just do a wave pulse, and a second one coming from the right. So it's going right to left, and a wave is going left to right, so wave A and wave B. Wave interference tells us that when two or more waves meet, they pass through the same region of a medium. They pass through one another without being altered. So in other words, A will continue going to the right, and B will continue going to the left, and they will not destroy one another or cause one another to turn around. But when they do get to the same point, what ends up happening is their amplitudes will combine, and they may create, in some instances, a larger wave, so A plus B. And we call that the principle of superposition. At any time, the combined waveform of two or more interfering waves is given by the sum of the displacements of the individual waves. Now, when two waves interfere, there's two possibilities for what we call superposition or interference. One is known as constructive interference. Constructive interference is when the two waves occur and the displacements are in the same direction. So to do a quick drawing, if I had a wave, two wave pulses, and one's moving to the right on the screen and one's moving to the left, and this has an amplitude of 1 and this has an amplitude of 1, when they arrive at the same region, we will get an amplitude of 2. And after the fact, they will continue to move on in their own direction. So this would be 1 after and 1 after. If this is wave A, this is wave B, and it'll look like they switch sides almost. This is called constructive interference. Destructive interference would be if we had a wave, let's say 1, we'll call that wave A, and it's moving to the right of the screen, and then we take a bigger wave, maybe of amplitude 2, and it's moving to the left, we'll call that wave B. When they get to the same region, we're going to add those displacements. One of them is going to be negative, so the end result is a -1 amplitude. And then after the fact, they're going to continue to move on as though they never encountered one another. So it's really when they only arrive at the same location that we get the superposition or the interference. After that, it's as if nothing has happened. And there's 1, so that's A, and this is B. So we have constructive interference and destructive interference. Now what I wanted to show you quickly is just an animation of that. If you look to the right portion of the screen, here we have a blue wave and a red wave, and those represent the individual waves, and they'll pass by one another as if the other wasn't even there. But the gray line represents the medium that they're traveling in. whether that's water or air. And if I run this simulation, what you can see is that they're going to combine and create a large wave. It's a little glitchy there. But, you can see a square and a sinusoidal wave adding. You can see the amplitudes add together. These are the two triangles that add together to create a larger amplitude. You can see that they add together. And really all you're doing is adding displacements. And then they pass through as if the other wasn't there. So the interference only really occurs for a brief moment in time. Destructive interference would mean that the two waves have different displacements, and you can see here, if I can get these waves at the exact same location, for a brief moment, the resulting amplitude will be exactly zero. It'll be almost like that wave isn't even there, but then as time goes on, we'll see them pass through one another. Here we have the sine wave and the square wave, kind of, it looks like one's eating the other almost, and then the two triangular waves coming together and flipping. So that's constructive and destructive interference. In the third part of the lab, we looked at waves as they reflected off of an object, and the first type of reflection that we looked at was something called fixed end termination, which is if you had the wave pulse and it were going to reflect off of a wall, so the string that the pulse is traveling through is attached to a wall, and that point cannot move. When the wave bounces back, it bounces back on the opposite side. So what we say is this is an opposite side reflection. If that end is free to move, it's a different result for a reflection. If the wave comes in, it will actually go back on the same side. So a same side reflection for free end termination. And for fixed end termination, it's an opposite side reflection. And what I want to do is just show you a brief example of that right now. If you take a look at these animations. So here's a person holding a string. It's attached to a wall, so it's fixed in place. On this simulation, we call it a hard boundary, but here comes the wave. It tries to move the wall, it fails, it reflects back on the opposite side. So the wave is really trying to lift up on the wall. For every force up, the wall pushes back down and flips the wave over. This is called fixed end termination reflection. We also have free end. In this computer simulation, they call it an open boundary. And if you look to the right here where I'm circling with the mouse, imagine that there's a pole and a ring is attached to it, and this ring can slide up and down. And when the person makes the wave pulse, it slides up, and then it comes back on the same side. And hopefully you got to see that in the lab. And if you didn't, I'm going to try to do the demonstration again. This is what we call a free end reflection. It reflects back on the same side. Side. So fixed end termination, opposite side reflection, free end termination, same side reflection. And finally, sometimes when we have a wave, it doesn't reflect off of something, it will pass through to a different material. Wave transmission is referred to as the passing of a wave from one medium into another of a different density. And what I actually want to do with this is I want to show you an animation beforehand and then draw the picture after. So if you look in this, where I'm circling with the mouse here, we're going to take a wave and it's going to go from a less dense material, a light string, to a heavier rope. And there's a couple changes that occur. The first one is that the wave will decrease in amplitude because this is a much heavier object and it's harder to lift it up. The second thing that's going to happen is that it's just not going to move as fast. So the amplitude is going to go down, the wave speed is going to go down, and the third thing, is that some of the wave does not make it through. Some of the wave bounces back, and it bounces back on the opposite side that it came in on. You could think of this heavy object as acting kind of like a fixed end, but not completely a fixed end. That's why some goes through we reverse the scenario and we go from more dense to less dense, so we have the wave in a heavy object and it goes to a light object, we'll see different results. We'll see an amplitude grow, we'll see a wave speed increase, and then we'll see a same side reflection. Nice and smooth. Help us a little bit. There's an increase in amplitude, increase in wave speed, and then a small same side reflection. We'll see it one more time here. Watch the amplitude grow, the wave speed increase, and a small same side reflection. So I want to just draw those things quickly here. I'm going to draw less dense. I draw as a string, put a little wave pulse. Here's our more dense medium. That's this right here. This is the less dense medium. And then I'll draw just a little amplitude. And then let me get a opposite side reflection. So three things. The speed decreases, the amplitude decreases, and then there's an opposite side. I'll write partial reflection. Not all of the wave is reflected, just some of it. It's like looking into the window of your car. You can look into the car, but you see that faint reflection of yourself. That's like a partial reflection. So three things that are happening when you transmit a wave from a less dense to a more dense medium. And then for the opposite case, really what it is if I draw the wave pulse going through, this is our more dense medium, going into something that's less dense, three things will happen. The amplitude will rise, the speed will rise, and there'll be a same side reflection. So I'm just drawing my little picture here. So let's see. The speed will increase. The amplitude will increase when it goes into the less dense medium, and then we'll get a same side partial reflection. So those are some of the basic properties of waves. We have wave speed. The amplitude does not impact the speed, but the medium does. Interference, we have constructive and destructive interference. Although the amplitudes will add up, the waves will continue to pass through one another. It's only when they're at the same location that they'll interfere. Wave reflection, you have fixed end and free end termination reflection. And then transmission, sometimes a wave goes from a less dense to a more dense medium. Sometimes it goes from a more dense to a less dense medium. And there's changes that occur for each.